This is a Legion week. So this week, I want to follow on from our discussion from 2 weeks ago, where we started looking at the distributed collectible objects. And so today, what I look at is actually some examples of using those to actually construct operate or construct data structures to represent the region trees and index space trees and index partitions and stuff like that. I'm trying to move in a direction where we will be able to shortly be able to start talking about some of the Legion dependence analysis and how that starts working. But we need some data structures first, like the region trees and index based trees and stuff to be able to describe that. And so to introduce those things, like we're going to look at those abstractions today, and then we'll also look at, those things are all going to be instances of the distributed collectible stuff that we looked at last time. And so we'll look at how some of the reference counting works on the region trees to be able to know when it's safe to reclaim objects inside of Legion, using some of the reference counting machinery that we looked at in the previous lesson. So, okay, so this is the region tree header file, and effectively it captures a lot of the abstractions that exist inside the runtime for representing index spaces and partitions and logical regions and field spaces and those kinds of things. There's one sort of entry point class for getting access to these various different things, and that's the region tree forest. I'm actually probably in the future going to refactor this class to get rid of it. It will probably just get merged into the main runtime class for Legion because it doesn't really provide much value over the existing runtime. It's effectively just like a subset of the runtime functionality today. But importantly, there's going to be nodes or there are methods on this class to get nodes for if given a handle from the application, like for an index space or an index partition, field space, logical region, you can get back the corresponding node in the region tree that's going to represent that particular abstraction, which is the actual data structure that backs all those handles that exist in a Legion program. So whenever you make an index space, you have one of these index space nodes inside the runtime that actually represents that and has all the metadata associated with it and so forth. And that's true of pretty much every kind of handle that you see in a Legion program, and for the things in the region tree, they all exist here. So just useful methods. There are methods in here also for testing whether you still have nodes and stuff like that. But these get node methods are the ones that you'll probably use most frequently for doing various different things. So useful to know that they're here. Okay, but more importantly, what are these index space nodes and index part nodes and field space nodes and region nodes and so forth? So they're all defined in this class, in this file as well. So for example, if we go look at index space node, this is what's going to represent an index space when you make it. And you can see that this is the index space node, but it's not actually the base class. So there's actually two base classes for this. One is sort of an index space expression, which we'll probably need to talk about in a future lesson. But an index tree node is just a node that exists in the index space tree. So it's like the common base class between either an index space node or an index partition, right? If you make a partition on an index space, say by calling create partition by star one of the partition creation methods, that will make an index partition node, which also exists in this file and also inherits from this index tree node base class, right? And so if we search for index tree node, this is the common base class for everything in the index space tree, right? And you can see this is where we actually get one of those distributed collectible things that we looked at the previous time. So this is this inherits from the valid distributed collectible class, right? And so that means that it has like an extra state in the garbage collection algorithm for it, for having an extra type of reference for tracking valid references. And I'll explain why that is today. But it is also a distributed collectible class, right? Just like we looked at in the previous lesson, so that these nodes can be referenced. There are copies of these nodes on multiple, copies of the nodes on multiple different processes, right? If you're running on a multi-node system, right? And so, doing the distributed reference counting and stuff all gets done with those distributed collectible objects like we looked at the last time. So it's useful to see how that all hooks together. Now, similarly, there are also classes in here for the field spaces, right? So there's a field space node class in here. And you'll notice this one only inherits from the distributed collectible class. So this one doesn't need the special valid extra valid reference kinds. It just needs the two kinds of references, and we'll see why that is also today. But this represents a field space and it has all the metadata associated with tracking. These field info structs will track all the metadata associated with every field that you allocate in this field space. And I'm not going to get into too much detail about field spaces and stuff today, but you can come take a look at that. Right, and then we've also got, for representing logical regions, we also have region nodes for representing logical regions, and you see this inherits from the common base class, region tree node, right? As in contrast to index tree nodes for the index base trees, right? And so there's also representing logical partitions, these partition nodes, and also inherits from this base region tree node. And if we go look at this region tree node class, right, you see this also inherits from distributed collectible here as well. So everything in here is going to be one of those instances of a distributed collectible object that can be reference counted using the machinery that we looked at in the previous lesson. Okay, so the interesting thing about this is how do you determine when we're actually going to look at how the reference counting actually works on some of these nodes, because it's useful to see how you actually clean up these data structures once the application starts deleting them and stuff like that. So in order to do that, let me show you the big scary diagram, and then hopefully by the end of the lesson we'll be able to actually understand it. So this is the diagram that represents the different kinds of references that are tracked on these index-based trees. And you shouldn't understand this at all right now, but by the end of the lecture we're actually hopefully going to be able to pick apart all the different pieces of this so you can actually understand what's going on. So just to make it clear what's happening here, there's an index-based tree here, right? So you got an index base with a partition here that has two subspaces, right? I'm sort of representing the partition with this sort of more bold black line here. Right, and then maybe one of those index bases has a further partition down here with some index base, subspaces off of it. Right, you've got a field space up here. You've got a logical region that's, effectively the combination of this index base with this field space to create this logical region. Right, and then you've got a corresponding logical partition for these things. And you've got references coming from the application, right? When the application makes an index base or an index partition or a field space or a logical region, right, those are effectively holding references. There's a reference held to all of these things from the application until the application actually destroys the corresponding object, right? And so when the application destroys their side of things, that will remove this reference, but that doesn't mean that this data structure actually disappears right away, right? These data structures are not safe to disappear until they're no longer needed. So you need to have all the reference counts go to 0 in order for the actual object to really be deleted. And so we'll talk today a little bit about how some of that works. As a brief refresher, you'll remember that there are three kinds of references in this graph, and I've denoted them with different colors. These are sort of the standard colors that I use for representing them. So just to refresh everyone's memory, right? A resource reference is effectively a reference that just says, keep the data structure from being freed in the local process, but that doesn't prevent it from being freed on other processes on remote nodes, right? So a resource reference is a really very lightweight reference that just keeps the object itself alive on this local node or local process without doing anything else. Now, a GC reference is stronger, right? And effectively it guarantees that the object will still be able to be referenced on remote nodes, right? So you can't collect any of the objects on any of the nodes until all the GC references are gone on all of the nodes, right? And so there's a collective sort of collection happening there where only when all the GC references are gone across all the nodes can you actually start collecting objects and going down to the local state, right? Which means you're only you've only got resource references left. Right, and then valid references are just a second level of this GC reference. They're like a second level version of those. And so you'd have to all the valid references on all the nodes have to be removed before you can go down and start trying to remove the GC or checking for the GC references are gone. Right, and so And you can only add these valid references to things that are instances of that valid distributed collectible class, right? So you can't do that to normal distributed collectibles. Normal distributed collectibles only have these two kinds of references, right? And then things that are valid references, right, can actually have that, can actually have valid references held to them to give us an extra state. And hopefully, but if we have enough time, we'll actually talk about why things in this index-based tree have to require these extra valid references, whereas things over here on the right do not. Right, and you can actually see this, right? Like we saw that, the index-based tree class over here, right, is an instance of valid distributed collectible, which means it can have valid references added to it, right? So that's where you can see things in this index-based tree have green things pointing into it, right? Whereas things over here on the right, the region tree, nodes, I should actually do these things, as well as the field spaces, right? They're just normal distributed collectibles. So there's no green references pointing to the any of the things over here, right? And so that's the corresponding, difference between, inheriting from distributed collectible versus valid distributed collectible. And if you do try to add a valid reference to one of these things, it will actually barf at you. Like the compiler will tell you can't call that method on here. So there's nice static type checking for that. So you can't really mess it up. Okay, so what's going on here? So let's try to write down, or at least think about what some of the invariants are for keeping alive, various things inside of this all these different data structures that we have to keep alive, right? So, just some basic ideas, like, as long as as long as one of these partitions is alive, right, then the parent index space for that partition also has to be alive, right? Like if the application could still reference a partition that it hasn't deleted, right, then ultimately, the things above it in that index space tree have to also be kept alive, right? Effectively, the application, creates root level index spaces, and then it creates these applications, these partitions, right? And these partitions, might still be able to reference up the tree from themselves, as well as down to their particular subspaces, right? But once an application deletes a partition, then it's not really safe for the application to reference that partition or any of its immediate subspaces, right? So what you can actually see happening here, right, and this is actually, somewhat intentional, right, is that, the application, we implicitly add these valid references to keep around the root index space as well as the partitions, right, as long as the application hasn't explicitly deleted them. When the application explicitly deletes these things, we don't actually go and delete, these data structures directly. What we do is we remove these references, these application references that are no longer needed. And so that, enables things to be potentially cleaned up once the reference count goes to 0, but doesn't immediately delete things. And in order to maintain this transitive property that I mentioned, where you might be able to reference up the tree if you still have a reference to this partition, right? We effectively add these valid references up the tree, to two things that the application actually has references on, right? So there's a reason that this reference here, going from this particular partition here up to this partition up here, right, skips these intermediate index spaces, right? Because these intermediate index spaces, these subspaces, can't actually be explicitly deleted by the application, right? They can only be deleted once this partition is no longer valid, right? And so, effectively, that's why this reference skips a level. And let me actually start showing you some of the code for, where these references get added, so you can tie this back in your head. So let's hop over here to the region tree. So
what if the application has a reference to the index space node itself?
You mean the one of these subspaces down here?
Yeah.
So we effectively keep those implicitly for you. So you can actually see these valid references that point from the partitions down to the subspaces, right, for this partition. And you can see that on both of these partitions, both these green arrows here pointing to the subspaces for the partition, right? So as long as this partition is valid, right, it keeps a valid reference on each of its subspaces, right? The application doesn't do that, right? There's no way if an application actually tried to explicitly delete these subspaces, right, we would actually give you an error, right? So the runtime says the only things that you can actually explicitly delete, are the things that you've actually made, right, which are either these partitions, right, or the root index spaces for the index space trees.
Okay, so if you delete a partition, then you shouldn't keep any references to the sub index.
That's right. Effectively, once the application deletes a partition, right, then all the subspaces of that partition, also lose their references, right? That's kind of like the invariant that we maintain. Now, it's a little bit transitive, right? We don't explicitly delete these index spaces, right? If you remove this reference, that doesn't immediately remove these green references. What that means is that once all the valid references pointing to this partition, all the green references coming into this partition are gone, then the partition will transition from the valid state down to the GC state, right? And that will remove these green arrows going out of the partition. Does that
Gotcha. Yep.
that make sense? And remember, this is a monotonically decreasing state machine, right? So you start off in the highest state that you can be in, right? And once all your incoming references at that state go to 0, then you transition down to the next state. Once all these references go to 0, then you transition to the next state. And once all these references go to 0, then you can actually delete the object, right? Yeah. And so, and you get these like, so let me actually show you where some of these references get added, and then also show you the state transition calls that you get and where you remove these green references like that happen to do those things, right? So, okay, let's actually look at some code. So we're actually going to look at the create node methods here. These are the methods in the region tree forest that actually make these nodes inside of the region tree forest, right? So every one of these nodes in here, has a particular create node method. And actually, in the case of like some of them, like index spaces, there are actually 2 variants of it. They probably should be refactored into one. So I have a create node, and you can always tell the thing you're making is like, the handle is the first thing that gets passed in. So we're making an index space node in this case. We're also making an index space node here, you're giving a handle and you're giving back the node. And there's ones down here for partitions and stuff like that. But we can just look at the simple logic for this one. There's a helper structure here to help create this, because ultimately this index space node actually needs to be a templated thing on its dimensionality and coordinate type. Let me actually just do a quick digression to show you that. So I mentioned that there is this index space node class, right? Which is like the base class for all index spaces to represent index spaces. But there's also a further specialization of this, which is the index space node T class, which is the templated version of this, which templates on the dimensionality of the index space and the coordinate type of the index space for this, right? And this is because Realm does all of its stuff with templates for handling index spaces. And so this is how we get into template land to actually be able to do templated calls for calling into Realm. So like every index space node class is just you'll see there's lots of pure virtual methods on here corresponding to all the different things that you might want to do on this index space, right? And they're pure virtual because this index space node class is just a base class, that needs to be specialized for a particular dimensionality and coordinate type. And so that's what this creator index space creator object is doing. It's helping to bring us into template land to actually create the index space node T. But that's a detail that you guys can go look at offline, and we'll probably talk about these NT template helper things in a future lesson. But for now, we're just making an index space node to represent this particular index space handle. There are races here in this creation process, and so the first thing we do once we get the lock to actually make this index space node is we check to see if somebody else has already made it. If so, we can delete the thing that we were making and return the one that's already been made. That helps us deduplicate, right? But once we've actually made this, right, then we can actually start to actually let's see, to actually be able to, to put this into this data structure, the region tree forest tracks for tracking all the index space nodes, right? And then we can start, we record if we have a parent in our tree, we record ourselves with that. Here is where we actually add the reference. This is actually the call that actually adds this application reference to this tree. So this is actually making this this like green arrow right here to put the reference in on for the index space, right? For the root index space. And then, let's see, if I can actually, let's take a look at index space node. Let's see, I'm trying to remember where we actually put these references. This is, that's actually adding this blue reference right here, sorry, from like, a subspace up to a parent index partition. Where did that go? Is it in the index space creator? It might actually be in the index space creator. Let's see here. Let me. Oh, I thought it was over here. Let's see. I'm trying to find where we add the valid references. Clearly did not get enough sleep last night. Just trying to, actually, let's look at the partition one because maybe it will be a little bit easier to track down here. Let me go back to create node. Index spaces, index partitions. Okay. So yeah, the index partition one is a little bit easier to track. So this is the case we're actually making an index partition here, right? And here's the application reference that, if we are the, effectively tracking that, if you make the partition, right, the application adds on a reference here. But we also add references up the tree, right? So like, effectively here's this if-else statement, right, is effectively handling the case of adding the valid references up the tree, right? And so, in the case where you have if your parent, which is your index space parent, right, for this partition, has a parent, which is also a partition, then you add the reference to that partition up the tree, right? And so that's this case where you're a partition that has a parent, which also has a parent, which is this partition. So you add this reference, up to the previous partition. That's this green reference right here. Right, but in the case where you don't, in the else statement, right, you just have a parent that's a root index space, right, then you add it directly to that. And so that's like, for an example, this partition here adds this green reference here up to its parent index space, right? Notice also that, for partitions, they also have a color space, right? And so you have to add a reference, from this partition to keep this color space valid, because you could still traverse up the tree for this color space is actually another kind of index space, right? It's just an index space in like a different tree. In fact, it could even be in the same tree, but most of the time it's in a different tree, right? And so again, like if you've got a parent on this color space, then you add it to its parent, right? Otherwise, you can just add the reference directly to the root index space partition. So that's this valid reference right here going to the color space for this partition. Importantly, like as you add children to this partition, so if we look at like the index part node add child, so like as you make these subspaces and you add them to this partition, as you register them with this partition as they get made, right? Then we actually add references to this child and then record it in our set of children, right? And so you can actually see these two references right here, right? So like as you make new index space nodes that are children of a partition, they get registered with this index part node, right? And then that adds the green and red references right here, right? Going down from this partition to the child, right? So we're effectively adding a reference to the child from ourselves, right? Using our distribute ID for this particular distribute collectible. Right, so that's giving you this nested reference down from these nested references down from the partition down here. And if you look in like the index part node constructor itself, you can see this is where we actually add these resource references. Too many lines there. Right, and that's where you're adding references like from this partition up to its parent index space, and that's just keeping this pointer valid, like the pointer to our parent index space that just keeps this object on this local address space from being deleted before we ourselves are deleted. So you can see these resource references going up the region, up these index space trees are effectively just like making sure pointers are always valid, right? They don't keep anything alive on remote nodes, but they just keep our pointers valid on this local address space. And so we hold those until like, if we look in the destructor for, index part node, right here, we actually remove like our references on like our parent and our color space, removing those resource references, right? That effectively just like, enables this to be these objects to actually be deleted, locally on this address space. And actually, now that I see this, I actually missed a reference in this diagram. So I missed the reference. There's also a resource reference here from this partition over to this color space over here. So there's a reference like that, also to keep that alive. Okay, so you can kind of see, the idea of these green references, coming back to the valid references, right? They're effectively keeping things alive that the application can actually see itself, right? So as long as, one of these index-based things actually has a green reference, that means that the application could potentially still need to refer to the handle for this thing, right? Either directly or indirectly via walking over the index-based tree in order to find that particular handle, right? So like if you haven't actually deleted this partition, then the application could still have a handle to this partition, and it could still walk up this index-based tree, up to the root, and need to be able to reference that. So like as long as these green references are transitively keeping alive things that the application could still reference on this index-based tree. Let me actually briefly step over here to the region tree, right, which is effectively the same principle is being tracked using the red references, the GC references over here, right? So as long as there are references, a red reference to one of the things over here, that's keeping it alive because it could still be referenced via some sort of access from the application, right? For example, like this field space could be accessed either directly from the application, or it could be referenced because it may have deleted the field space, but it might still have live logical regions, that need to reference that field space, right? And so we keep a red GC reference, from every logical region to its field space to make sure that, the application could still refer to this field space as long as there's at least one logical region that refers to this field space that's keeping it alive, right? And so the same invariant is kind of being maintained over here. And we'll see the difference of why index-based trees need this extra level, why it's being tracked with green references, valid references over here, and only with GC references over here, hopefully before the end of the lecture. Okay. So effectively, the red references are doing the same thing over here that the green references are doing over here. Is that part at least clear before we start talking about what the red references do over on this side? Gonna take that as a yes unless somebody has a major question. Okay.
I'm just looking forward to understanding the difference between.
Yeah, what the differences are between them. Yeah. Well, actually, maybe I should do that first if that's actually going to be clarifying. Okay, so let me actually try to tackle that first to help clear up that mystery, and then maybe we'll come back and fill in the rest of the references on this diagram to understand what's actually happening. Okay, so the tricky thing about these index-based trees, right, is that index spaces, serve a dual purpose inside the runtime. One is they're useful names for the application for sets of points, right? So like they're the application can reference these things and still be able to refer, to be able to use them to compute other index spaces and use them in their application, stuff like that. The other thing that they are used for is they are used by the runtime analysis to do its analysis on figuring out dependencies and stuff like that. And in order to do that, let's go over here to this other slide over here. The index spaces can also be, parts of computations. Okay, and what that means is that the runtime, and we're going to see examples of this at a future date. The application or the runtime will often need to compute, set expressions on index spaces. So like Legion will often take two index spaces, right, and maybe compute an intersection between them, and then maybe compute a difference of the original index space with the intersection. Right, do that on both sides, and then maybe you union the differences together to compute, the complement set or something like that, right? And so Legion can do all sorts of computations on index spaces as sort of like atoms of set arithmetic, right? Like these are like the base sets, right, that are defined by the application, but Legion often computes additional things on these index spaces, right? And we actually call these things index space expressions, right? We actually saw that over here in the code. So let me actually, refresh. We saw this earlier. We go look at index space node, right? In addition to being an instance of an index tree node, right, an index space node is also an instance of this index space expression class, right? And this index-based expression class is also a distributed, well, everything that is an instance of this is also a distributed collectible, but this index-based expression class is sort of a base class that represents computations on index spaces, right? So it can either be, a base, like effectively there are two things that inherit from this index-based expression class. One is going to be the base index or the index-based nodes, and the other are these index-based operations, right? So we've got index-based nodes inherit from index-based expression, and index-based operations inherit from index-based expression. And so what you can see is like these index-based operations are going to be these set operators, right? Whether it's intersection or difference or union, right? You can see the various different kinds of operation. There's a couple other special cases, but mainly there are these three different things. Now, the reason to have the tricky thing about this is that we want to make sure that Legion will also need to keep these expressions alive as part of its analysis long past the point where potentially this index-based tree actually needs to survive, right? So we may need to be able to globally reference like intermediate index-based nodes in these index-based expressions, right, and keep them alive across lots of different nodes. But we don't want that to imply that we keep these, keeping alive just like an intermediate index space in this index-based tree as part of one of these expressions over here. We don't want that to keep like the whole tree up above, this index-based node alive as well, right? Like we don't want that to occur, because that'll also, like, if you keep this partition alive, then it keeps all those other subspaces alive and so forth, right? And so like we kind of want index-based nodes to be decoupled from the rest of their, the index-based tree stuff, right? But we still need them to be able to be kept alive globally, in case they're needed for the analysis, right? And so this is the reason for this sort of two-level reference counting here, right? So you effectively want to keep index-based nodes alive on like across all the nodes where it's needed, with these red references, but you don't want that to imply that you keep alive all the index-based tree and stuff above here, just because some random index space is used in an index-based expression over here and needs to be kept alive. We don't want that to keep alive the rest of the index-based tree, right? And so that's the reason for this two-level thing, right? So the green references are keeping alive the index-based tree sort of relationships, right, associated with what the application actually cares about, whereas the red references are just keeping index spaces themselves alive across the nodes, right? So that they can't be collected, but without preserving the index-based tree invariance, right? You don't see any red references over here going up this index-based tree graph, right? They just kind of come across and then they go down, from the partition. And the reason for that is that, mostly the reasons that you see red references on index spaces actually come from these index-based expression computations. So I'm not sure I explained that particularly well.
How are these expressions? I remember you had told me a while back that you try to avoid emitting dependent partitioning operations like these as much as possible, defer or cache the results.
Right.
So I assume that's why these are not duplicated and these become distributed collectibles, because you want to compute them once, right?
That's right. Some of these things, like intersection is actually pretty cheap to compute, but differences and unions are much more expensive, right, for Realm to actually compute for these things. Right, and so we do want to deduplicate those computations and keep these, these expressions that we've computed alive. Like if you are going to pay for doing a difference or a union, you don't necessarily want to just throw that away as soon as you're done with it, right? You kind of want to remember that. So Legion often will remember these, it'll remember these intermediate, computations that it's done, as long as the base index-based expressions are still alive somewhere in the system, right?
And how does the application keep a reference? Let's say I assume the user asked for that union somewhere in the program.
No. So these are actually unions that are computed by the runtime. So effectively anything that the application computes will always have a corresponding index-based node, right? So if it's something that the application has done, then it will always have a name, like a handle, right, associated with that index space, right? And it will have an index-based node that the application can refer to, right? So these things are things that the runtime is doing itself internally as part of its analysis.
Mhm.
Right.
So
And
if the user did like partition by difference or something,
that would
or
actually create
whatever.
new index spaces. And I mean, the expressions, let's see. Yeah, we don't even we don't even make an index space expression for those things today. We actually are creating a new index space that will actually have its own name over here in the index space tree graph, and um, and and then and then it will be its own node. Now there is a little bit of trickiness here, right? Which is, I mean, I'm giving you guys a lot of stuff without showing you any code, but there is an algorithm. Effectively, before we do any like intersection, right, on two index spaces, the first thing that we do is like we always look, or even if we're doing like a difference between an existing intersection and another index space, right? The first thing we do with either of these two things is we actually get a canonical index space, or we get a canonical index space expression for these things. So there's actually like some deduplication to detect if, like say for example, like you intersect these two index spaces, and the intersection of these two things is the same as this index space, right? So like this one is dominating this particular one, so therefore the intersection between them is the same as this one, right? So when you actually go to do like this difference, like we'll actually notice that there's actually a check to see, like the first time you use this intersection, we'll actually do a check to find the quote unquote canonical index space expression for this intersection, which effectively is like a congruence test, right? It checks to see like, we have this new node here in this expression graph, but does it have the same value as one of the prior expressions that we've already computed, right? And if so, we can actually use that to sort of deduplicate computations, because maybe we've already done some difference of this this thing with itself, right? And so like I can show you this code very briefly since we're talking about it. So this code, like let's actually look at the intersection. What is it called? Intersect index spaces. So this is a method on the region tree forest, right? And it takes two of these index space expressions, right, and it computes a new index space expression for the intersection of these two things, right? And so these index space expressions, right, they could either be, right, an index space node, or they could be some other priorly computed expression, right, that you've computed somewhere in here, like another index space operation. Right, and so if you actually look in the code for this, we're in region tree.c. Yep, here we go. Intersect index spaces. There's some very simple cases here, right? If they point to the same thing, then the intersection is the same, right? It's easy. If either one is empty, right, you can return the other one, or return it right away, because like anything intersect with empty is always empty. But then you see these two methods right here. You get these canonical expressions, right? So before you actually do this index space expression, you do this thing to find the canonical index space expression, right? And so what that does is it says, like, for like these arguments, is there some other prior index space, right, or something that we already know about that has exactly the same set of points, a congruence test for doing these things, and that's actually like helping to deduplicate some of the math, the set expression math that has to happen for these things, right? And so that actually helps save you some of the computation, right? Does that answer your question, or make things more confusing?
So it sounds like there's a couple levels of caching, right? So the caching you just talked about is, have I seen, or can I reduce this tree locally, let's say, and then if I decide that no, I really need to compute this, then essentially I will ask the owner to do the operation and use that use that as a distributed collectible. Have that like index space expression node as a distributed.
Yeah, we only make new things in here when we absolutely have to, right? Like we haven't computed something before. Right. And
crucially, this is only for internal runtime things.
Exactly. Yes. Yeah. Right. And so these things in here, these index space operations, right, that are unions and differences and intersections, right? They're only visible to the runtime, right? And so we only want to keep them around as long as like the index space is still alive somewhere in in the system, right? Like the thing, only if like the index-based operations that, or sorry, index-based nodes that contributed to their computation are still alive, right? That's what these red arrows are sort of referring to, right? Effectively, as long as this index base still has a red reference to it, to keep it alive, right? Then that will keep all the computations that are derived from that index base alive. But as soon as one of these goes away, then the things through here will start rippling and starting being collected.
So when you refer to the index-based world, basically it's just a legion object that is part of the region tree, right?
That's right.
Mhm.
Yeah, that's right.
Mhm.
These are legion index spaces, not realm index spaces that are values, right?
And where do you actually store them? Some kind of like dynamic table or something?
Well, yeah. So I mean, all these are just malloced on the heap. Right? So like all the nodes, all the various nodes that we've been looking at here, like yeah, index-based node and stuff are all just allocated on the heap to be able to and they live on the heap in the local address space, and you can have copies of them on different nodes, right? So like there might be an instance of this index-based node for a particular handle on multiple different nodes, right? But they'll have the same realm index space and stuff like that.
I got it. Okay.
So since we're in this picture,
Yeah.
Can you explain the blue arrows that are going reverse?
That's right. So like effectively they're just pointing, they're keeping the local copy. These are just, anytime you see a blue pointer, right? Effectively those are keeping pointers alive. So like let's actually look at like if you look at like the index space operation class. Let's see here. Actually, you might need to look at the specific index space operation. So let's actually look at like here's union. So here's the index space union, and you see it's an instance of index space operation T, which was up here, which is an instance of index space operation. Sorry, here's index space operation T, right, which is an instance of index space operation. Just making that relationship clear. And you see what it has. It has this vector. So this is the index space union class, and you see it has this vector of the sub expressions that were contributing to this union. And what these blue references here are doing are just keeping these pointers alive, right, inside the local node, right? So like as long as this object hasn't been deleted off the heap, right, it keeps an index space. It has pointers to these index space expressions down the heap. That doesn't mean that these index space expressions are prevented from being collected on other nodes. It's just keeping these pointers alive, right, inside this vector. Right, so these blue references effectively are what is keeping those pointers alive. To make sure that they're still valid. Like even if this index space, on this node has had all of its red reference gone away, and it's been marked as like, effectively it can't be referenced, safely on remote nodes, the object itself is still alive on the heap, here, as long as these things are still alive, right? As long as these references are still held, and that keeps the pointers alive, so that you can still refer to the pointers even though this index space might be in the process of being collected globally, right? Does that make sense?
So I guess my question is, generally about the resource reference scheme, is it just there to keep things in a valid, or how should I say it, in a valid but undefined state, kind of as garbage collection is happening?
Yeah. So
because you can't actually query the index space, at that point, right?
Right. So the way to think of it is like, as long as somebody is holding a red reference to one of these things, right? Like these distributed collectibles you could then pack the handle for these distributed collectibles and refer to it on a remote node, right? So as long as you have a red reference, that means that you can still send a message to another node and be able to refer to this handle on that remote node, right? So it's still like a liveness property of knowing that handle or it can still be referred to on remote nodes, right? Because like if any node has a red reference to one of these things, that means that it's still alive globally, right? Anywhere in the system you could refer to that handle, and the runtime will figure out what to do. But as soon as all the red references are gone, right, then what that means is that it's safe to start, for the runtime to start just collecting, right, via the distributed collectible object, these objects on remote nodes once, all of their local references, the blue references have gone away, right? So the blue references are like local only references. They just keep the object alive on the local node, right? Which mean that like your pointers are valid and effectively, it's still alive on the heap, but it's not safe to necessarily pack up a handle and move it to a or refer to that handle on a remote node. So like the red references are stronger. They keep the object alive globally, whereas the blue references, like, they just keep things alive on the local node, like on the local heap.
But once an object has reached blue state, then it's just time to collect it. Like you can't.
That's right.
Like you can't reliably ask for information about it anymore. Right? It might be on a different node, and you can't do that anymore.
Your pointer is still good on the local node, right? So like you can still talk to the object. The object hasn't been deleted off the heap. You're not going to get like a seg fault, right, for dereferencing pointers pointing to things that you hold a blue reference to. And that's useful for like, sometimes you still need to refer to stuff as you're in the process of like cleaning up one of these like objects here. We sometimes still need to refer to things of the index-based node that, on the local node that, that were part of the computing this difference, right? And so this pointer still needs to be valid from the difference back to the base index base that it was computed on, right? And so that's what this blue reference does, is it keeps that the local heap allocation still good. But it's no longer safe to then refer to like the handle on a remote node for this index space, because you don't know that you've still got like a red reference there.
Yep.
Right. So yeah, and you can see these blue references, one thing that's interesting about this graph is that, and this one too, right, is that you'll notice in here, you can never draw a cycle with any of the references of the same color. And this is actually what Legion GC actually checks, right? So like, effectively, it'd be very bad if you can draw a cycle with the same color of reference. But it's okay to have cycles of different colors of references, right? Because effectively what is that like, once, like say, in this case, like once all the green references to this index partition are gone, then that partition will transition from the valid state down to the GC state, and it will remove all of its green references to other stuff. Right, and so then all the green references will further fall away, right? So as long as you don't have any cycles with green, then you're good. And the same thing is true of red, right? You can't draw any cycles with red in this graph, right? So as long as like all of the, red, like once all the incoming red references are gone, then the distributed collectible will transition from the red reference state to the blue reference state and remove its red references, right? And you can actually, let me just show you those methods in here so you know what to look for. So like, so for example, there's the notify invalid. Here's like the example of the notify invalid method. This is when so for example, this is on the index partition node. So when it transitions from the green, from a valid state down to the GC state, right, effectively it gets this callback from the base distributed collectible class saying notify invalid, which effectively says you're transitioning from this green state to this red state. And you can see it will go through and remove all of its green references. So here it's removing like the color space references here, like removing, this green reference, this color space here, right? It's also going to start removing, the valid references to either its parent, right? So that's either removing this green reference here if you're in the case of this partition, or removing this green reference here in the case of its partition, right? So effectively it gets this callback and it also removes like the valid references on all its children. So that's removing these green references here, right? To effectively get rid of those. So as it transitions from green to red, it removes all of its green references. And then similarly, there's the notify local method down here, which is effectively the callback that you get when you're transitioning from the red state down to the blue state. Right, and again, it's removing its red references, right, on its children, right, and so forth, right. So you can effectively find, these state transitions here on all these different objects that are instances of these distributed collectibles, right. And it holds that effectively, those you can effectively you'll see that there's no cycles on any of the particular kinds of references, right. One other thing that's worth, since we're running out of time a little bit here, let me actually call attention to one more thing over here, which is useful thing to understand this, and that's this partition tracker object. So there's one like really tricky thing that happens here, which is like logical partitions. So not index-based partitions, right? Index-based partitions are made by the application, right? And so the application explicitly destroys them when they're done with them, right? Logical partitions are weird. They're not explicitly made by the application. They are effectively exist right in this world where, as long as the logical region, the root logical region that the application made, right, exists, then the logical partitions exist as long as this logical region exists, as well as this particular index-based partition exists, right? And the idea of this partition tracker is actually to be able to remove, effectively keep these logical partitions alive as long as two things are true, right? As long as the logical region still is alive, right? Still, has a global reference, is still in the red state, right? Or as long as this index partition is still in the green state, then this logical partition will continue to live. But as soon as either one of those two things are no longer true, right, then we want to remove this like global reference keeping this logical partition alive. So this partition tracker is kind of like an OR. It's like, as soon as either one of these two things changes its state, either from the green state in the case of the index partition or from the red state in the case of this logical region, then we want to remove this red reference from the logical partition. So this is a little weird. This is like an OR object, right? It's effectively saying as soon as one of those two things is no longer true, then we know that this logical partition no longer needs to have this this global reference from here. And so you can actually see this partition tracker object. So, effectively, it's expecting two. It's a little bit of a weird thing because it needs to live as long as this object itself needs to live as long as like both of these references are here and could be removed. But it's only going to hold this reference as long as both of those references are there. So like effectively, like when you remove this partition reference, you check to see if you're like the first one to actually do the removal, and if so, then you're the one that actually goes and does the removal of this GC reference from the logical partition to keep alive, right? And that will allow for a collection of this logical partition as soon as either the index partition is no longer valid or the logical region is no longer globally valid, or not, I shouldn't use the word valid, but globally alive. So that's kind of what's going on with this particular part of this here. Yep. Okay. So let's see. To summarize, let's see. I'm trying to think if there's anything else worth talking about in the limited time we have left about this index-based expression stuff. We are going to encounter these things a lot more because like when we start to do runtime analysis, we're going to need to do things like intersections and differences and unions of existing application level index spaces. So expect to see more of these calls. Like let me just point you guys here at this. Where'd it go? Nope, I need to type properly. Right, so you can see there are methods for union index spaces, and you can either do pairwise or you can give a whole set of them. Same thing with intersecting index spaces. You can do pairwise or give a set of index spaces to intersect, right? And then there's subtract index spaces, which will actually, subtract you off or take one index space expression and subtract another one. And we are going to see uses of these internally inside the runtime. So we're going to use these kind of primitives a lot, but these are effectively things that are runtime only, right? So like these index space expressions are only visible inside the runtime. They don't actually have names that the application could refer to. This is actually one of those things like, you guys may have encountered this somewhat in the mapper where like, I know Manolis has often asked me to give oftentimes the mapper can ask for like, is an instance valid for a particular logical region? The answer is partially, right? And the reason for that is the runtime, actually has an index-based expression that says what the valid set is for like an instance. This instance is valid for some of the data in this logical region, but not all of it, right? And so the runtime has these internal index-based expressions that might represent like a partial index space. But it's not clear, whether it's worth exposing those kinds of things up to the application yet. And we haven't actually had a good use case for doing that quite yet. But this is the reason why I've kind of deferred from doing that so far. Okay. Are there any questions for today? I know it was a bit of a whirlwind tour. I'm happy to share these pictures and stuff with you guys more, and discuss questions or comments you have about them.
I have just one question, and
Sure.
I would be interesting to just learn about the implementation of distributed collectible, but I believe that was one of the previous lectures, which I must have missed, right? So
It was the
is that
previous
important?
Legion one before this one. Yep.
Okay, sure. Probably just go ahead and look at it.
Yep. So I'm hoping that in the next Legion lecture we're actually going to start trying to do some program analysis, which will actually take place on these index base and region trees and stuff like that. And so it's useful to be familiar with like the actual data structures themselves that exist, to represent the things that you make in a Legion program before we actually start walking over them and doing stuff. But yep, here they are. Okay. Any more questions for today? All right. Next week, Sean is going to be here to talk about stuff in Realm. So see everybody next week.